Hi, I'm Randall Heyman, a university mathematics academic. I was concerned about student learning being impacted by the coronavirus outbreak. So I've created a number of Corona help playlists, actually with no YouTube ads, to make it even easier. So these are where educators or students have requested me to do a video on some mathematical problem or concept, or just some mathematical chat. And I'm set up now to do these videos pretty quickly, so I can turn them around rapidly. So if you'd like me to do a video for you or your students, then comment me or email me and I'll try and help you out. And it doesn't matter whether it's primary school, secondary school, or tertiary school, or university level mathematics. I'm happy to have a go at trying to help you out. So someone's asked me about principal ideals. So I'm going to do, this will be one of two videos on principal ideals. I should just say to people, I've done quite a lot of videos on abstract algebra in the last 2 to 3 weeks. You shouldn't expect from me more than what I'm doing. I'm responding to what people are asking. I'm not putting together a properly well thought out, comprehensive study into abstract algebra. So I'm only explaining the things that I need to explain to get to a certain point. So in this case, principal ideals. And I'm skating over quite a lot of stuff that you really need to know if you're going to go on further and further into abstract algebra. So at this stage, in all the videos I've done so far, I haven't talked about important concepts like homomorphisms, isomorphisms, quotient groups and quotient rings, cosets and things like that. So I just thought I'd say that because I've been doing a lot on abstract algebra and it just sort of needs to be said, I think. Okay, so let's talk about principal ideals. And here I've got a definition. This is from the book by Freilich. So let's work through it. If R is a commutative ring, so remember commutative ring means that it doesn't matter which way you multiply elements in the ring, it doesn't matter. So in the ring of integers, that's just saying that 7 times 3 is the same as 3 times 7. And it's the same no matter which integers you pick. We've got it, in this case, we've got unity. So this is a ring with unity. This is the multiplicative unity. In the ring of integers, that's the number 1. It's special because if you multiply 1 by any integer, you get that integer. It doesn't change it. Okay, and it's saying, okay, let's take some element of the ring. So you might want to think here, let's at this point think R equals the integers and A equals, say, I don't know, 8. Okay, then the ideal, so this ideal is all here, here. It's all the elements, so A equals 8. So here we're thinking of the set of R times 8 such that R is an element of the integers. That's what we're thinking in our mind. It's the principal ideal generated by A, which is 8 here, denoted by this. So what we're saying is that so this is an ideal, and it's a principal ideal generated by 8. And of course, this is just the numbers, negative 16, negative 8. It's just all the integers multiplied that are divisible by 8. So it's a pretty simple concept when you look at the integers. Okay, so I'll do what's another example? Here's one. We'll call it this, the ideal generated by X in, let's call it the reals, the polynomials with real coefficients. So remember, this is the set of A0 plus A1X plus up to AMX to the M, where all the AIs are real numbers and M is an integer. I suppose it's an integer, or positive integer, I suppose, including, I'll just include 0. So M's just a positive integer. So that's all the polynomials. Now, what is this? What is this back here? What is this? Well, so what is X? X, the ideal generated by X is just the set of all the polynomials times X, where P, all these polynomials, are elements of the ring. And I'll just write what it is. What is this? If we multiply all these polynomials by X, all that we get is, we basically get all polynomials with real coefficients excluding, actually, I suppose, with F0 equals 0. I think that'll do. P0. P0. Sorry, I should actually move the whole thing up so I can write a bit neater. P0 equals 0. So all polynomials with real coefficients where P0 equals 0. So example, well, x cubed plus 5x. Well, that's just the product of, that's just in the language of what we've got here, that's just the polynomial x squared plus 5 times x. See here, we've got the times x. Another example, 22 on 5 x squared plus pi times x. Let's make that to the power 21, and this is 11. Well, that is just equal to 22 on 5 times x to the 20 plus pi times x to the 10, all times x. But what about this one, x squared plus 1? Well, I can't express that as something times, you know, some polynomial here, some p here times x, because I've got that constant of 1. So it doesn't equal that. So this x squared plus 1 is not in this ideal that we've created up here. So I hope that has given you some insight into principal ideals. So what I'll probably do in the next video is because someone's asked me particularly about principal ideals in things like Z11 and Z15, and I'm not going to necessarily do these exact ones, but I'll do some to I think it was actually 14. It doesn't matter. I'll do something around these rings in the next video.